So this is what we are looking at. This is the second part of the presentation. So what we did in the first part of this lecture was we derived expressions for the messages from the variable nodes to the factor nodes. This was beta nk, and then this was rho nk. So these are the two messages that we derived already. So now let's look at what are the messages from the factor nodes to the variable nodes. This is, to refresh your memories, the general situation for any factor graph. So this fk is a factor node, and it incorporates a function which is, I've used the same notation fk for the function 2, and so it maximizes something over all variables m not equal to n. So we are looking at the message that this factor node fk sends to Vn, and this summation is the sum of all incoming messages from the variable node to that factor node, excluding n itself, excluding this n here. So the sum of all these messages is taken, and then we have this functions which is global, which also includes Vn as well as all of these, and we maximize over all of these except Vn, and that gives us the message mu fk to Vn when Vn equals 1, and separately when Vn equals 0, and then we do the subtraction which get the scalar mu fk to Vn. And this is what we are going to apply to all the messages that we will examine now. So first, eta nk. Now keep in mind that pay attention to this here, and this also keep in mind. I'll not refer to it, but this is explicitly what we are dealing with. So now we are dealing with this in. This is the factor node in to any variable node cnk. Now remember, this in here accounts for the 1 of n constraint in this row. Now the arguments to this in are the decision variables in row n, which includes all these cnks, including cnk and cnk prime. They're not, I've used two separate nodes here, one for cnk and one for cnk prime. Cnk prime can be any other node except cnk, because cnk is fixed here. I'm considering the message from in here to cnk. Now the decision variables in row n except cnk, so everything here except cnk are included in this summation here, as well as what this maximization is being carried out over. It's not being carried out over cnk, because we have except cnk here. This cnk is fixed. It's not being maximized over. So let's look at when cnk equals 1. So eta nk1 is equal to this expression here. In when cnk equals 1, and the summation over all the other incoming messages. K prime is not equal to k. Now suppose cnk prime equals 1. So we are looking at eta nk 1. So cnk equals 1. This is 1. And suppose there is some other k prime for which this is also 1. So that's a constraint violation, because Cnk equals 1 implies that k is the exemplar of n, but when this is also 1, it means that k prime is also an exemplar of n. So n has two exemplars, k and k prime. This row corresponds to point n, right? So this is a 1 of n constraint violation. Whence in will be equal to negative infinity, because for any constraint violation, in has to be negative infinity. If there is no constraint violation, then in will be 0. So now let's look at when Cnk prime equals 0. That's the other situation for all k prime not equal to k. So this Cnk is still a 1. We are looking at Cnk is 1, but everywhere else we have zeros. Everywhere we have zeros in this row. Whence in will always be 0, because if with only a single 1 here and everything else being a 0, the constraint can never be violated. So ink is equal to 0. Is equal to 0. Whence eta nk1 is this maximum here. But now we are looking at all the other Cnk primes equal to 0. This is the condition, right? And there is nothing to maximize over, because these are all fixed at zeros. All the variables are fixed. Whence we can remove the max operation and we get this expression for eta nk1. So now let's look at the situation where Cnk equals 0. In other words, point n does not choose point k as its exemplar. So this is our expression for eta nk when Cnk equals 0. We are fixing Cnk at 0. Now we'll consider this situation first. There is some other k prime such that Cnk prime equals 1. This means that the point n corresponding to this row, the nth row, has picked k prime, some k prime, to be its exemplar. This Cnk equals 0. So this is our situation. And for all other points L, the C and L is 0. So everywhere we have zeros. This also is a 0, but we have a single one at some k prime. So Cnk prime for some k prime is 1. This situation. Whence this is valid, because we have a single one in this entire row. Therefore, in will be equal to 0. The constraint, 1 of n constraint, is not violated. Whence this in becomes equal to 0 because the constraint is not violated, and so eta nk0 is given by this expression. I've singled out the beta nk prime for which Cnk prime is a 1, because there is one k prime such that n has picked k prime as its exemplar. Now, for all other configurations, suppose we have all zeros, or we have 2 ones, or 3 ones, or any other configuration, we would land up with in equals negative infinity, because that would lead to a constraint violation. So that's because n doesn't have a unique exemplar. It has either no exemplar, or it has multiple exemplars, including k prime. So since this is a 1 of n constraint violation, it will be negative infinite. And when we do the maximization, this negative infinity can never be the maximum. Whence we can eliminate this possibility, so that this becomes our expression for eta nk0. So now we have expressions for eta nk1 and eta nk0. So let's derive the scalar eta nk, which is the difference, and eta nk1 minus eta nk0, which is given by this expression here. The red and the blue correspond to this and this term here. That's the blue term, second one. And then what I do is I'm splitting this summation into uh, the one containing k prime and the one not containing k prime here. That's the summation over all else, where this k prime is the argmax of this quantity here. So this is what I have. Now observe the blues and the reds here. So this term and this term are identical. So we cancel them. And then I bring this beta inside the max because it's constant. So we get this expression for eta nk. Negative max of beta nk prime 1 minus beta nk prime 0, which is equal to, because this by definition is beta nk prime. So this is what I land up with for eta nk. So this is the new expression that we derived. Now we'll look at alpha. First, we'll look at alpha kk. By the way, alpha, as it'll turn out, is the same thing as the availability message of the affinity propagation algorithm. And if you remember, we had different expressions for the self-availability and the cross-availability alpha nk. So we'll look at self-availability first. In other words, we'll concentrate on alpha kk. So alpha kk is given by this expression. It's the maximum over all n's except k itself of this function ek, which is over all variables, including k itself, ckk, and this summation of the incoming messages from all other n's except k. So this is the expression for alpha kk. This ek is the exemplar consistency constraint factor node for column k. This is the column k. And like I just said, this summation takes place over all CNKs except CKK. And that's what this maximization is carried out over. Whereas the arguments to this function ek include both the CNKs and the CKK2. Okay, so this is our expression for alpha kk. And since it's important, let's keep that in mind. So now we'll look at alpha nk when n and k are different. N is not equal to k. So we have this expression for alpha nk c and k. And since it's important, let's keep it in mind. First, let's consider the situation where c and k equals 1. Always keep an eye on this block here. So when c and k equals 1, n selects k as its exemplar. That's when c and k equals 1. So k must be an exemplar. If n selects k as an exemplar, then k itself must be an exemplar, which means that ckk has to be a 1. Otherwise, there would be a constraint violation. If cnk equals 1, but ckk is 0, what does it mean? N is picking some k as its exemplar, but k itself is not an exemplar. Otherwise, so that's the case. If this were 0, it would mean a exemplar consistency a constraint violation. So ckk must be equal to 1. Whence alpha nk1 is given by this expression here. This is cnk equals 1. And I'm removing the ckk1. It's fixed outside this maximization. So it's this expression here, which is equal to this maximization now. Instead of doing the global maximization, I am doing maximization locally over each c n prime k's. So I'm considering both situations, c n, k, n prime k equals 0 and when c n prime k equals 1. So let's remember this expression for alpha nk1. So now let's look at alpha nk equals 0. When cnk equals 0, what does it mean? It means that n has not picked k as its exemplar. Now we'll look at two further cases here when ckk equals 0 and separately when ckk equals 1. So n has not picked k as its exemplar and ckk equals 0, which means that k is not an exemplar itself. If ckk equals 0, this is 0, so k is not an exemplar, which means that this entire column k must be all zeros to avoid a exemplar consistency constraint violation. So k is not an exemplar. So every element cn prime k must be equal to 0. Otherwise, the exemplar consistency constraint would be violated. Whence alpha and k0 is this expression here, we forcing all the c and k's to be zeros here. So this ek, when everything is a 0, this ek will be a 0 as there will be no consistency constraint violation. Since there is no maximization to carry out over because all these c's are fixed at zeros, so we remove it, and so what we are left with alpha nk0 is given by this expression here, and let's keep it aside. Now we'll look at the case where, well, cnk is 0, but when ckk is an exemplar. Although n is not selecting k as its exemplar, k is an exemplar itself. So that's when ckk equals 1. So cn prime k can be 0 or 1. It doesn't matter. The exemplar consistency constraint would never be violated because ckk equals 1. So we can choose zeros and ones everywhere else. Whence this expression reduces to this because ek, we reject all the cases of exemplar consistency violation. Well, it'll never happen in this case, ek equals 1. So this becomes equal to 0. Ek, this function, is 0. And so this is the expression, max of all of these. And since alpha kk1 is the specific situation that we are considering, ckk equals 1 is what we are considering. This 1, so this rho kk1 is fixed. We remove it outside the maximum. And so this is the expression that we land up with. Cn prime k can be 0 or 1, and this maximum, instead of carrying it out globally over all of these Cn prime k's, we do it locally, separately for each term. So this is an expression which we need to remember. Now we look at alpha nk0. In the general situation, we looked at when ckk was equal to 0, and separately we looked at the case when ckk was equal to 1, and we landed up with these expressions. So alpha nk0 must be the max of this and this. So it's equal to max of, so this is the first first expression here, and this is the second expression. Let's keep it aside. So now we have expressions for alpha nk1 and separately for alpha nk0. We take the difference between the two, that's alpha nk, the scalar message alpha nk, which is equal to, we replace them with alpha nk1 and alpha nk0 expressions. This is what we get. And now I'm going to use this identity here. Everything in red is this x. This and this, well, including this. So this and this are the x's, and this blue here is the y. So I'll replace the left-hand side with this expression on the right-hand side of the identity. Observe. So we get this. So this is the right-hand side of the identity. This is what we have. So next, what I do is I split this summation into two parts. I take rho kk outside the summation, and then I move rho kk over here. And observe, I have rho kk1, and this is the rho kk0, which I obtained from here. And so rho kk1 minus rho kk0 is the scalar rho kk, whence I get this expression here. So this is that expression, which is equal to, what I do next is, if you observe this summation, I have the same variables the summation is being carried out over. So I group the two summations into a single summation here, as in this expression. So now what I'll do is I'll use this identity. Everything red is this x here. So I have max of x, and this is y, blue is y, is equal to max of y minus x0. So this here expression, this actually it's just this expression inside this summation is equal to this in the identity. So we replace it with the right-hand side of the identity. We get this, max of y minus x comma 0, which is this, which is equal to this expression here, because rho nk1 minus rho nk0 is simply rho nk. I should have said rho n prime k. and it's got its usual interpretation. So this is the expression for alpha nk. So I have in place all 5 expressions that I need. These are all the messages of the factor graph. Now we are in a position to derive the rules for affinity propagation. These are the set of expressions that we have for the factor graph model. Now, alpha here is the availability and rho is the responsibility. These are the 2 sets of variables used by affinity propagation clustering, and therefore we need to eliminate beta and eta. These are redundant messages. We have to keep only alpha and rho. So we separate out the terms, and since alpha does not include any of the redundant variables, beta and eta, we retain the expressions as they are. Now, rho nk is equal to eta nk plus snk, which is equal to snk plus eta nk. I just swapped the 2 terms on the right. Next, I'm using this expression here to replace eta nk with this term. So I get this expression for rho nk. I've replaced eta nk with negative max beta nk prime. Now beta nk prime is given by this expression. This is beta nk. I replace k with k prime and do the replacement here. So this is my expression for rho nk. This is an expression for rho nk, and observe that it does not contain eta or beta anymore. So I have in effect removed the redundant messages. So this becomes my final expression for rho, the responsibility variable. So these are the update rules for affinity propagation clustering. So this is the affinity propagation clustering initialization, and then we do this for every point n, and then for every exemplar k, we carry out these operations simultaneously, and then after the termination condition is satisfied, we pick out the exemplars. And this is the same affinity propagation algorithm line by line as the one that we had introduced a few lectures ago. The end.